Okay, good morning, guys. Get things a little bit organized here and we can get moving. So today we're going to talk more about power series. Specifically, I'm going to show you guys how to come up with power series for a meaningful size class of functions. The goal at the end of chapter 11 here is for me to be able to give you just about any function and you to be able to come up with a power series for that function. That's where we're going. There are a bunch of different tricks for this, but the one I'm going to show you today is kind of the primary trick. However, before we dive in, I wanted to look at one or two problems just having to do with intervals and radii of convergence. So let me flip on the dot cam. We can get started. Okay. Yeah. Okay. That's right. This pen has been arguing with me lately, so we're going to look in black today. All right. So today, a few things. A little more 11.8 stuff. And then an intro to 11.9, which is finding power series for functions. So I'll remind you what I said last time. You do have some homework this week from section 11.9. I'm going to split 11.9 over 2 weeks because there's kind of really two parts to 11.9. 11.9, the first part is all using algebra and geometric series to get power series for a given function. And then the second part of 11.9 is differentiating and integrating power series. So I didn't want to straddle you with too much this week. I didn't want to saddle you with too much this week, sorry. I didn't want to give you the integration and differentiation of power series at the same time as kind of just introducing the core concepts of power series. So that will come next week. But the rest of 11.9 we are going to cover. We're going to cover it today. Before I get there, though, I wanted to do just a few more problems from 11.8. So if you don't mind, some of these I showed you the other day. Some of these are not hard. The sort of convergence business we've looked at. Right. So these examples are good. Definitely make sure you're comfy with these examples and sort of the basic things that they describe. But I wanted to look at some of these more challenging examples here. So on all of the 3 through 28, you're just going to run the ratio test. You're going to run the ratio test and then check the endpoints. But 29, 30, 31, these are the sort of things that that we looked at a little bit, but we haven't looked at too much. So I'm pretty sure I did something like this for you guys last time. I'd like to do something like this for you guys today. That'll be our last little bit of 11.8. So suppose I have a power series. Of the form Cn x to the n. So the center is 0. Converging when x is equal to, let's say, -3, and diverging when x is equal to positive 5. And I'm going to come at this a little bit differently than they do in that problem. I'm going to ask two questions. What is the smallest possible IOC? Remember, IOC stands for interval of convergence. It's the interval of x values for which the series converges. And then the other question here, what is the largest possible IOC? So we know that the interval of convergence is an interval symmetric about 0, right? Always symmetric about the center of that series, and this series is centered at 0. So the series sigma n from 0 to infinity cn x to the n has center a equals 0. So the IOC is symmetric about 0. The endpoints, could be included or not included, but I mean that this is an interval of the form negative r to r, right? Like negative 5 to 5, negative 3 to 3, negative 2 to 2, something like that. Could not be like negative 1 to 7, because the center of that interval is not 0. So if we wanted to write that down, the endpoints of the IOC are negative r and r, where r is the radius of convergence. Now, the fact that the series converges when x is equal to negative 3, what does that tell you? So here's the real line, here's 0, here's negative 3. If the series converges when x is negative 3, what can you tell me about negative 3 as it relates to the interval of convergence? Yeah, good. Good. Did everybody see Maggie's chat remark there? Negative 3, I like the way you said it the first time, is within R of 0. In other words, this number, negative 3, has to be in the IOC. Right? Because the interval of convergence is all of the x values such that the series converges. And this series converges when you plug in x equals negative 3, so negative 3 has to be in the IOC. So the IOC could extend out past negative 3, or it could extend just to negative 3. This is your sort of worst case scenario, that negative 3 is one of the endpoints for the IOC. So it's not an interior point of the interval, but it's still in the interval. In other words, we know that r, the radius of convergence, has to be at least 3. Could be bigger, but worst case, r is exactly equal to 3, and that endpoint negative 3 happens to be included. If r is exactly equal to 3, and we know that if r is exactly equal to 3, and we know that negative 3 is in the IOC, then the right endpoint has to be positive 3, and the worst possible case is that positive 3 is not in the IOC. So here my interval of convergence would be this. So the smallest possible IOC is the left closed, right open interval -3 to 3. Is everybody following that logic? These tend to be the hardest problems from this section. Just wanted to spend a second chewing on this for you. The series is centered at 0, which means the interval of convergence has to be centered at 0. -3 is known to be in the interval of convergence because I'm told that the series converges when we plug in x equals -3. So it's the smallest possible interval centered at 0 containing -3. Well, how tightly can I shrink in centered at 0 and still contain -3? Well, that would put my left endpoint right here. I can't bring that left endpoint in any further because then -3 wouldn't be in the interval. If I bring it out any further, then it's not as small as possible. So the smallest possible IOC, if I start thinking of all the intervals symmetric about 0, and I just shrink this sumbitch in until I make it as small as possible, I have to stop here because I need this to be inside, which means it has to be the interval -3 to 3. And then if I want to be a real asshole about it, I can kick the +3 out. Nobody told me that the series converges when x is +3, just that the series converges when x is -3. So my smallest possible interval is this. I'll pause again here for questions. Is there anything we want to ask about this? Just to be clear, this would be our solution for part A. All right, so that's our worst possible case, smallest possible IOC. What's the best possible case? What if I wanted to start here and expand outward? How far can I expand outward until I get to something I know is not in the interval of convergence? Can anybody tell me a number that is for sure not in the interval of convergence? 5. Yeah, good. Series diverges when x is equal to 5. So 5 is not in the IOC. So if I'm thinking, how far can I expand outward before I hit something that's definitely not in the IOC? Let's say 5 is right here. I know that 5 is not in the IOC. So the furthest I can expand to the right and not include 5 would be like this. Which would mean r, my radius of convergence, must be less than or equal to 5. And in the maximal case here, would run from -5 up to 5. Like that. Remember, I'm looking for the biggest possible IOC now. So when I think about this other endpoint over here, I want to include him. So the worst case, or sorry, the best case here would be that r is exactly equal to 5. It could be smaller, but if I'm asking what is the largest possible IOC, I want to ask what's the biggest r could possibly be. R has to be less than or equal to 5. Can't be bigger than 5, because if r was bigger than 5, then this endpoint would be further out here, and then 5 would be in the IOC, but we know that 5 is not in the IOC. So this means that our largest possible IOC is the left closed to right open interval -5 to 5. It would be this stuff. Now, why am I doing this? These questions don't necessarily look like the question I said I was going to solve. This is the stuff you need to do in order to solve those sort of questions. So I could ask you, what could you tell me about the series sigma cn 2 to the n? So the sort of questions that I would ask on a test here are, what can be said of sigma n from 0 to infinity cn times 2 to the n, or sigma n from 0 to infinity cn times -6 to the n. Well, this one is my series with x equal to 2 plugged in, right? Sigma n from 0 to infinity cn x to the n, sigma n from 0 to infinity cn 2 to the n. So this is this with x equals 2 plugged in. And even in the worst possible case, 2 is inside the IOC. So with the information they gave me, I could say this series must converge. And similarly, this guy is my series with x equals -6 plugged in. And even in the best case, -6 is not in the IOC. Therefore, this series must diverge. So these are fun sort of questions that can be asked and discussed regarding the shape of the interval of convergence. So even in the largest possible IOC, -6 is outside, which means that if you plug -6 into this series, it must diverge, just based on the information we had up there, because that's what led us to drawing these. And even in the worst possible case, 2 is inside the IOC, so this series must converge. These are fun questions. I did put both of these in your homework. And when you get to the question that looks like number 30 here, when you get to this guy, you need to take the information that's given in that sentence and do what I did here. This is how you will come up with a definitive answer to those questions. And I may well ask you on the exam, what is the smallest possible interval of convergence given some set of information like that? Or what is the largest possible interval of convergence given some set of information like that? Or I could just ask you the thing that they ask you in the textbook, right? Just what can you tell me about these series? And then require you to back it up. In any of those cases, you would need to do an analysis like this. Last call for questions on this guy. Okay. So then, I'm going to start talking to you about section 11.9. The title of this section is Representations, or Representing Functions as Power Series. And the whole game in section 11.9 is to begin with what I will refer to as the geometric series trick. Which is really simple. It's the thing you know. It's that 1 over 1 minus r is always sigma n from 0 to infinity r to the n. That is the geometric series trick. So any function that you can write in this form, you can immediately write a power series for. You have to sort out the interval of convergence, which you'll get by solving this inequality. But the important thing is this. So like the obvious example, if I wanted to find a power series for the function f of x equals 1 over 1 minus x, this is easy. Just take r equal to x. And you see 1 over 1 minus x has to be sigma n from 0 to infinity x to the n. That's it. That's the power series for that function. So here the center is 0 and the coefficients Cn and the coefficients Cn, they're all just 1. And it's boring. It's just plugging in, taking this formula and plugging in x for r. Kind of next level of examples here. Same business, find a power series for f of x equals 1 over 1 minus 2x. What do you think we're going to do here? Good. Yeah, here we'll just take r to be 2x. So we get 1 over 1 minus 2x equals sigma n from 0 to infinity 2x all to the n. But this we should clean up a little bit because we want to be able to read off the center and the coefficients easily. 2x all to the n is the same as 2 to the n times x to the n. So here, the center is still 0, but the coefficients, the Cn's, are 2 to the n. So everybody see this? Without too much work, you can see that I can get a series for anything of the form 1 over x minus r, or 1 over, I shouldn't say x minus r. Let me work another example here to drive home this point before I try to talk in general. Let's find a power series for f of x equals 1 over x minus 5. This is going to be a little bit more work. it's not immediately obvious what I should choose for r, because it's not 1 over 1 minus something. All right, so far all of these are like 1 over 1 minus something, 1 over 1 minus something. This is 1 over x minus 5. So I can't take r to be 5. That doesn't make sense because this isn't a 1. So I need to do some algebra. Here's the algebra we're going to do. First, I can force factor out a negative. Remember, a minus b is the negative of b minus a. I'm using this fact. I'm using this fact to force out a negative. Go ahead and distribute this negative. You'll see you get negative b plus a, which is the same as a minus b. And now my next move, I'll continue this down here. My next move is going to be to bring out the negative. And then I need to make this spot a 1. Well, I can make this spot a 1 by force factoring out a 5 from the denominator. So I'll have negative 1 over 5 times 1 minus x over 5. And now the 5 I can bring out also. This is negative 1/5 times 1 over 1 minus x over 5, like that. All right, so this 5 comes off as a 1/5. And I'm just writing these parentheses here to emphasize that x over 5 is a single chunk there. So what am I going to use for r here? Very good. This piece is now 1 over 1 minus something. So I can take r to be x over 5 and use my geometric series trick. So I'll get here that this is negative 1/5. That's this constant coming along for the ride. And then my 1 over 1 minus r piece is sigma n from 0 to infinity, x over 5 to the n. And again, we can clean this up. This is negative 1/5 sigma n from 0 to infinity, 1/5 to the n times x to the n. I'll leave the negative outside here, but I'm going to bring the 1/5 in because it'll interact with this. This is negative sigma n from 0 to infinity, 1/5 to the n plus 1 times x to the n. Good shit, right? So what's my center? Center is 0 still. And the Cn, the coefficients here, are negative. You can leave the negative out front or you can bring it inside. Either way is okay. I would write it like this: negative 1/5 to the n plus 1, like that. In the series, it looks prettier to leave the negative outside. But if we're talking about the coefficients, really I should include this negative. And finding the interval of convergence for all 3 of these examples is very easy. You just solve the inequality absolute value of r is less than 1. You could also run the ratio test, but it's not necessary because each of these is really just a geometric series. All right, look at this. This is a geometric series, definitely. This is a geometric series, definitely. The fun comes when you start integrating and differentiating these things. That's when things get exciting. But because I know this is a heavy week for you guys, I don't want to give you too much. Questions on any of these three examples? In this guy, there's nothing special about 5, right? If this 5 were a 3 or a 2 or a pi, the exact same shit would have worked. 1 over x minus c would always have a power series that looks like this, just with a c there instead of a 5. You know that if you're given any rational function, ratio of polynomials, you can factor them, right? You factor the denominator and then you can do partial fractions. And you can split any rational function up into sums of things that look like this. What that means is you can use this geometric series trick together with partial fractions to come up with a power series for any rational function. That's a big fucking deal. Rational functions are a huge family of functions. So if you're willing to be patient and run some partial fractions, you can take any rational function as long as the bottom factors into distinct linear factors and write it as a power series. Now you know that not every rational function has a denominator that factors into distinct linear factors. Sometimes you have irreducible quadratic factors. So with that in mind, let's try to find a power series for 1 over 1 plus x squared. Because you know the irreducible quadratics, you can always complete the square and get them to look something like this, like 1 plus x squared, or 5 plus x squared, or 5 plus x minus 2 squared, something like that, something whose shape is this. Does anybody see a way I can start writing this as 1 over 1 minus r? It's not quite that though. If I just use x squared as r, that would give me 1 minus x squared down here, right? 1 over 1 minus x squared. That's not what I have. But something very close to that will work. I think we'd all agree that you subtract a negative, that's the same as adding. It's important that the square here is not outside the parentheses, right? This is negative of x squared, not negative x all squared. Those are different things. But if we think of it like this, then I can take r to be negative x squared. And we'll get f of x is equal to sigma n from 0 to infinity negative x squared to the n, which is the same as sigma n from 0 to infinity negative 1 to the n x squared to the n, which is x to the 2n. The center here is still 0 because x to the 2n or x to the n, that's still like x minus 0 to the n. The coefficients now are a little bit more complicated because these aren't necessarily the numbers that match up with x to the n, they're the numbers that match up with x to the 2n. So the cn's here are a little harder to write down. If I was being careful about this, here's how I would write them down. I'm only going to do this once. Actually, we'll do it again when we talk about sine and cosine series. These are equal to 0 if n is odd, and -1 to the n if n is even. Actually, I should say if n is odd. Yeah, that's good. If n is even. Actually, no, it's not that simple, right? So if n is 0, that's even, and this is 1. If n is 1, that's odd. Oh, no, it doesn't work like that. Yeah, so this would be actually -1 to the 2k if n equals 2k. Yeah, let me try this one more time. I want to show you exactly what I mean. I don't want to confuse you with this stuff without explaining it. So let me write out the first few terms of the series. When n is equal to 0, we have -1 to the 0 times x to the 0. That's 1. And then when n is equal to 1, we have -1 to the 1 times x squared. And then plus x to the 4 minus x to the 6 plus x to the 8. So all the odd-powered terms are missing. So if we wanted to be really careful about writing this out and getting a formula for the CNs, which is something that's going to matter when we move into 1111, I'd write this as 1 plus 0x minus 1 times x squared plus 0x cubed plus 1 times x to the 4 plus 0x to the 5 minus 1 times x to the 6 plus 0x to the 7 plus 1 times x to the 8. So C0 is 1, C1 is 0, C2 is -1, C3 is 0, C4 is +1, C5 is 0, C6 is -1, C7 is 0, C8 is +1, and it would go on and on like this. So what's the actual formula for my CNs here? You get where I was coming with this, right? Cn is 0 if n is odd. C1 is 0, C3 is 0, C5 is 0, C7 is 0. And on the evens, it alternates. So I would say that it's -1 to the k if n equals 2k is even. Strictly speaking, those are the coefficients here. Because the evens alternate, right? C0 is 1, C2 is -1, C4 is 1, C6 is -1. So here, k is 1, here, sorry, here k is 0, here k is 1, here k is 2, here k is 3, here k is 4. And you see it follows the sign of k. Now don't panic if this last part is scary. If this stuff down here is scary, don't worry. You don't need this stuff for this section. You do need the stuff from here up. That's the stuff you need, and that's the stuff that's optional. If you're able to wrap your mind around the optional stuff, it will help you in the next section. But for right now, and I know there's limits to how much we can cram into our brain in a given day. Right now, the stuff I need you guys to be comfy with is the stuff up to here. All right. I need you to be comfy with this step, and with writing out these first few terms. I will address this stuff again when we get to section 1110 next week. So first, questions on the need bracket. Is there anything in here that feels weird that you guys would like to discuss? Are we comfy with this step? Comfy with the algebra? And then this stuff? Any questions there? Okay. Any questions or anything you guys would like to discuss under the optional bracket? Anything here that I could help clarify or make easier to understand? Okay. Let's do one kind of more thing along these lines here. I'm going to call this function g of x because it's closely related to the function f of x above. So I'd like to find a power series for x over 1 plus x squared. And we just found a power series, mind you, for 1 over 1 plus x squared. Any ideas what we could do here? Yeah. Would you guys agree that this is the same as x times 1 over 1 plus x squared? Yeah, when we multiply those things, we just multiply straight across. And 1 over 1 plus x squared has this power series. So this is x times sigma n from 0 to infinity, negative 1 to the n, x to the 2n. And now the reason I'm showing you this is because I want to show you what we can do with this x. This x doesn't have any n's in it. It's just an x. So with respect to the series, this is a constant, which means it can move in and out of the series at will. So I can shove that x inside the series. This is now x times negative 1 to the n, x to the 2n. And these things are all being multiplied. X times x to the 2n is x to the 2n plus 1. Nifty stuff, right? So I'm going to pause here for a second, and in a minute I'm going to switch over to the dot cam, or not the dot cam, to Desmos, and I want to kind of show you guys something, make some observations about power series in general by looking at these two explicit examples. Let's make sure everybody's caught up writing. About 5 more seconds. Okay. Let's explore a little bit. Oh, should alternate, right? Yeah, minus, plus, minus, plus, okay, 2, 4, 6, 8, 10, 12. This is a start. So I'm going to come in here and focus just on a part of this graph, because the interval of convergence for this series is just -1 to 1. And I'm going to, well, let's just give a few more terms here. Minus x to 14. Oh, shit. Plus x to 16. Minus x to 18. Plus x to 20. Minus x to 22. Plus x to 4. Minus x to 26. All right. So here's like the alternating series for 1 over 1 plus x squared all the way out to x to the 26. Compare the blue and the red. I think last time actually I had the partial sums in blue and the actual function in red. So let's do it like that.
Can you, I can't see Desmos.
No? Okay, here, let me, sometimes the screen share is a little wonky. Turn it off and turn it back on again. There, is that better?
Yes.
All right. So the red, that's 1 over 1 plus x squared. That's the function whose power series we found up here. And I'm just writing out the partial sums for this series, 1 minus x squared plus x to the 4. I wrote out a big, long partial sum for that power series here. And you notice if we pay attention just to the interval -1 to 1, the blue does a good job approximating the red on that interval, right? The blue and the red stay really close to each other. What kind of function is the red function? What sort of symmetry do you see in the red function? Anybody? Is this an even function, an odd function? Neither? Good. Yeah, Zach and Maggie are both right. It's symmetric about the y-axis, symmetric about the line x equals 0, which is the y-axis. So it is an even function. What do you notice about the terms of this power series? What sort of powers of x are showing up there? Even powers. Yeah. You ever wonder why we call even functions even and odd functions odd? The power series for an even function will only ever have even powered terms. The power series for an odd function, let's see. Our prototype odd function that we've been playing with here so far this morning is this one. What does a partial sum for that guy look like? Well, that was -1 to the n, x to the 2n plus 1. So that's x minus x cubed plus x to the 5 minus x to the 7 plus x to the 9, on minus x to the 11 plus x to the 13 minus x to the 15 plus x to the 17 and so on. Let's go out similarly far. All right. Same game. The interval of convergence for this guy is also -1 to 1. And if you look at the red function here, what kind of symmetry do we see? Origin symmetry, right? So this is an odd function. The red function here, x over 1 plus x squared, is an odd function. And its power series contains only odd terms. So there's a neat take-home message here. That stuff up out of the way. Yeah, the neat take-home message here is that an even function will have only even powers of x in its power series representation. And also, an odd function will have only odd powers of x in its power series representation. So if you're trying to find a power series for an even function and you end up writing something down which has some odd powers of x in it, you know you made a mistake. Conversely, if you're finding a power series for an odd function, you end up with some even powers of x in it, you know you made a mistake. It's not terribly hard to prove that if you start with a series that only has even or only has odd powers of x, that the resulting function will be an even or an odd function. But the converse is a little bit harder to prove, saying that if you start with an even function, its power series will only have even powers. Or if you start with an odd function, its power series will only have odd powers. But it is true. So this is one of those exciting things that we're able to discover now. All right. The last thing I'd like to do before I let you guys go today, we've looked at lots of these. Yeah, I really should prime you, get you ready for this idea of integrating and differentiating the series. Yeah, because that's really the rest of this. There really isn't anything else to do here. So what I'm about to show you, you don't need for this week's homework, but you will need it for next week's homework. Given a power series f of x, and I'm going to call it capital F here, is sigma n from 0 to infinity. I'm just going to assume for now that we're centered at 0. If I write out all the terms, that's C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the 4 and so on, right? This is just a shorthand for this big long sum. this big long sum looks like a polynomial. So you can differentiate it like a polynomial. I'll show you the full formula next week where we work with an arbitrary center. But the C0 term here is going to differentiate to 0. C1 times x is going to differentiate to C1. The derivative of x is just 1. C2 times x squared is going to differentiate to C2 times 2x. C3 times x cubed is going to differentiate to C3 times 3x squared. C4x to the 4 is going to differentiate to C4 times 4x to the 3. And so on. In other words, you can take the derivative of a power series one term at a time. Just differentiate each term individually. Each of those derivatives is a power rule derivative. But then you can put this back into sigma notation. I have here my CNs, and then instead of C2x squared, I have C2 times 2x. Instead of C3 times x cubed, I have C3 times 3x squared. Instead of C4 times x to the 4, I have C4 times 4x cubed. The pattern here is that you have Cn times n x to the n minus 1. You just differentiate the x to the n piece. But there is one other little catch. The n equals 0 term went away. Our series now starts at 1. Integration works the same way. The integral of the series, I would integrate C0. That's going to integrate to C0 times x. I would integrate C1x. That's going to integrate to C1 times x squared over 2. If you integrate C2x squared, that would become C2 times x cubed over 3. If you integrate C3x to the 3, that would become C3 times x to the 4 over 4. And if you integrate C4x to the 4, that would become C4 times x to the 5 over 5. So an antiderivative for a power series would look like sigma n from 1 to infinity Cn, from 0 to infinity. This time the index doesn't change, 0 to infinity. Cn times x to the n plus 1 over n plus 1. So again, you just integrate the x to the n term. The catch here is we need to put a big plus c out front because we're doing an indefinite integral. Again, I'm going to show you guys the full formulas next week. You don't need to panic about this right now, but I wanted to introduce it so you've seen what this process looks like at least once before we do it properly next week. And I want to give you a reason why. I want to show you something cool here. First, any questions about where either of these two formulas are coming from? This for the derivative or this for the integral? All right, if not, here's our little treat for today. One of the series on your last exam has a special value. I asked you to approximate, recall from exam 2, the series S equals sigma n from 0 to infinity, -1 to the n over 2n plus 1. This was the series where I said, tell me how many terms I need to approximate accurate with error less than 0.01. I claim this series is equal to pi over 4. And if you've gone through your test with me in office hours, when we got to that problem, I think I've done this for 2 or 3 people now. I showed you how your comparison, the thing that, the n value you gave gives a decimal, and then I showed you the decimal for pi over 4, and they were really, really close. Well, how do I know that this series has that value? How the fuck could I possibly know that if you add up the alternating reciprocal of the odd integers, you get this irrational number pi over 4? We begin with 1 over 1 plus x squared. This is the series that we just found a minute ago. This is sigma n from 0 to infinity, -1 to the n, x to the 2n. Now, if I integrate on both sides, here I'll get c plus sigma n from 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1. Right? Same way you would integrate x to the 2n if it wasn't in a series. You add 1 to the power and then divide by the new power. Add 1 to the power, divide by the new power. On the left-hand side, the integral of 1 over 1 plus x squared is the inverse tangent of x. So the inverse tangent of x is equal to some constant plus the sum from 0 to infinity. I'll write it like this, -1 to the n over 2n plus 1 times x to the 2n plus 1. I'll be able to show you that this constant is 0. Plugging x equals 0 on both sides. We see that the inverse tangent of 0 is equal to c plus this piece comes out to 0. I'll have to show you why this piece comes out to 0, but it does. Since the inverse tangent of 0 is 0, we get 0 equals c plus 0, which means c itself has to be 0. So the inverse tangent of x, the arctangent function, has a power series expansion. We just found it. It's the sum from 0 to infinity, -1 to the n over 2n plus 1 times x to the 2n plus 1. Plug x equals 1. Then you'll get the inverse tangent of 1 equals sigma n from 0 to infinity, -1 to the n over 2n plus 1 times 1 to the 2n plus 1. But 1 to the 2n plus 1, I'll do it down here. Arctan of 1 is pi over 4. And because 1 to the 2n plus 1 is just 1, you get sigma n from 0 to infinity, -1 to the n over 2n plus 1, which is what I claimed. This is probably the coolest and most powerful trick we have for summing interesting series. It's to recognize them as certain values of a power series for a function that we know. This is a really cool trick, and it's used all the time. A similar trick is how you show that 1 over n squared. When you add all of those up, you get pi squared over 6. And all of the other times in this semester when I've said, oh, this series, I happen to know for reasons I can't tell you yet what the value of this series is. Every time I've said that, I'm using something like this. So this is after your geometric series, which we learned, how to play with today. This is your next sort of important power series. And I'm going to be giving you a bunch of important power series as we proceed through the rest of chapter 11. There will be power series for sine, cosine, e to the x, and a few other things. These you'll be expected to remember. So I just wanted to conclude with this today, kind of give you a little bit of a treat or something, like something cool, like why have we been doing all this shit? Well, this is why we've been doing all this shit. For one, this will allow us to solve problems that before we could never solve. Like, what is the integral of sine x over x? Before then, no dice. But soon we'll be able to do that by writing sine x over x as a power series and then integrating the power series. Lots and lots of things like that, which before were totally out of reach, we can handle now, or we will be able to handle after our next class. But for now, I want you guys focusing on the 11.8 and 11.9 material that doesn't include any integration or differentiation. So it's really very straightforward. Just use the ratio test to find the intervals of convergence. Make sure you check the endpoints. And then in 11.9, all the work that you have to do this week is just the geometric series trick. So just the 4 or 5 examples that we did today. Precisely the same sort of thing. Work hard on those. And then next week, we're going to do lots and lots of stuff like this, where we integrate on both sides, usually starting with the geometric series, and then we'll integrate, and that will give us something new. This will get us series for the natural log and for a bunch of other kind of cool functions like arctan. After that, we're going to learn Taylor's formula, which is a somewhat complicated looking formula that'll tell you how to find a power series for pretty much any function. But the formula is a little bit difficult to use, so we're going to need practice using it. That is it. That is all I have for you guys today. Any questions before I let you all go? Okay, cool. Yeah, I hope you guys have a lovely weekend. Try not to stress too much about the election. Remember, people are people, no matter what stupid stuff anybody says. If they're your friend before, they should be your friend after. Take care.